understand the concept of measuring uh, chemicals. We use a proper amount of ingredients, any kind of recipe that you take at home, and whether you're filling in your gas tank, you always need to know a certain amount of fuel will fill in your gas tank. So there is somewhat a kind of accountability with the ingredient measured. In chemistry, we use a term that is called as a mole. A mole is a very specific term that is used mainly. A mole is a term that is used mainly to understand what amount of substance is present. In other words, when we use the term dozen, a dozen implies to you that it's a number of 12, which means it could be a dozen roses, a dozen donuts, a dozen pencil. You understand that it's a collection term that is used to specify a certain number of an item. Similarly, another example that you can see up here is a ream of paper. A ream is always considered to be 500 sheets. A case quantifies a number 12. So these would be terms that are used to specify the number of a substance. In chemistry, we use the term moles to count very tiny particles. So we are either measuring or counting, I should say, atoms, molecules, or ions. Any of these tiny molecules or atoms or ions can be counted by, and the count is considered to be a mole. And there is an amount of what this count will be. This count of a mole is going to be a very large number, and that number is 6.02 10 to the power 23. So whether we are taking a mole of carbon atoms, which would mean that there are 6.02 10 to the power 23 atoms of carbon, or a mole of sodium atoms, or a mole of gold atoms. We can also use the term mole to count the number of molecules. So whether it's a carbon dioxide, which is a molecule, or a molecule of water, each will have the same number of molecules, which is 6.02 10 to the power 23. This collection is considered to be a value which is given to you up here, and this number is called as an Avogadro's number, based on an Italian physicist who calculated this very, very large number. So you can pretty much take out the decimal and see what a large number this is. So Avogadro's number is used for a collection of items, of atoms, molecules, or ion. So anytime you indicate a mole of a compound, then that will be considered that mole would be 6.02 10 to the power 23 of the particular type of particle that makes up that compound. Now, the mole over here, for example, in an ionic compound, here we have sodium chloride and potassium sulfate. So when you say a mole, it's going to have that many formula units of that particular compound. Now, a mole can also be expressed as an equality. So here is your equality that is written to you. A mole is 6.02 10 to the power 23. You can convert that into two conversion factors. We learned this back in the dimensional analysis chapter. So let's see how this problem is done. Up here, it's read as how many copper atoms are in 0.50 moles of copper. So notice I've placed 0.5 mole of copper up here, and then I times it to my conversion factor. Again, I have many times repeated that this unit over here has to match the unit on the bottom on your conversion factors. When those two happen, then you cancel these out, and now you're expressing the number of atoms present in 0.5 moles of copper. Now, using Avogadro's number, we can also convert particles of substances to mole. So, for example, a question reads, how many moles of carbon dioxide are present in 2.50 and 10 to the power 25 molecules of carbon dioxide. Notice I've done the same thing. I've got my molecules up here, and I've got my molecules on the bottom. In this particular case, I'm using this part of the conversion factor and setting it up to cancel my molecules and expressing my answer in the number of moles. In the previous example, let's go back and you can see up here I used this part of the conversion factor. Okay, now that we know what is a mole, which is a quantity of dozen apples or a dozen roses or a dozen pencil or a dozen cantaloupes or a dozen egg do not weigh all the same. So when you take a mass of a mole, then that is called as a molar mass. So that is a mass of 1 mole of any compound expressed in grams. And the way this is done is fairly easier. We usually use the atomic mass of an element to express that as a molar mass. So, for example, 1 mole of sodium would be equal to the atomic mass of sodium, which is 107.9, and you can round this off for this class purposes as 108. For carbon, then 1 mole would be 12 grams, and 1 mole for sulfur would be 32 grams. Fairly simple. So now imagine if I had asked you to go and get 2 moles of carbon dioxide or 2 moles of carbon powder. Now you can almost see up here there's a powder up here. 2 moles would have the quantity, if you do the count, then the count will be 6.02 10 to the power 23 for 2 moles. Actually, this is for 1 mole, so we'd have to almost, let me erase this. Okay, so 1 mole of carbon dioxide is 6.02 10 to the power 23. So if I want to do 2 moles of carbon dioxide, then I would have to set it up in which I have 1 mole on the bottom and 6.02 10 to the power 23 on the top. I cancel these out, and my value, if you do your calculation with your calculators, it should come out to, let me just do it up here. Which comes to almost like 1.2 10 to the power 24, I think, if I did my math correctly on the calculator. So it's a very large number. Now, it's very hard for you to count these number of atoms. However, it will be very easy for you to weigh 2 moles of carbon dioxide if you knew what 1 mole of carbon dioxide weighs. So, for example, carbon has an atomic mass of 12 plus 16 times 2 for oxygen. So that is 12 plus 32, which is going to be 44. That is 1 mole of carbon would be 44 grams. 2 moles of carbon would be 88 grams. So if you go and weigh 88 grams of carbon dioxide, then it's going to have that many large number of moles of carbon dioxide. Hopefully it is making sense to you as to what I'm talking about. We will take the quantity and convert that into mass and mass into quantity. So here is another example in which we see the molar mass of a compound that is shown to you is calcium chloride. And calcium, since there are 1 mole of or 1 atom of carbon, its atomic mass is 40. Chlorine, there are 2 atoms, so that each atom is 35. 35 times 2 is 71. 35.5 times 2 is 71. And the total will come out to 111 grams. So that is 111 grams of, would be the molar mass of calcium chloride. Now, let's look at formulas to understand clearly how to do our mathematical calculations. Now, in a formula that we have done, we've already studied that a subscript in a formula basically tells the relationship of how many atoms are in the formula. So, for example, this is a molecule of glucose, and you can see there are 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. We can also express that as 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. So if you took the total of this, which would be carbon I'm sorry, I accidentally went too fast on the, let's go back over here. Okay, so if we go back and now let's say 6 moles of carbon, you would have 6 times 12, and then you would take 12 times 1, and you would take 6 times 16. And if you total those up, that comes to 180 grams, which would be the formula weight for glucose. Now, subscripts we have learned are used for conversion factors. So if you really want to use, you want to say the relationship of the number of carbons per a formula, you can express that. So for example, here's a formula of aspirin. Aspirin is C9H8O4. So notice I've taken a relationship of 9 moles of carbon for every 1 mole of the molecule of aspirin, 8 moles of hydrogen for every 1 mole of aspirin, 4 moles of oxygen for 1 mole of aspirin. Or you can do it the other way. So pretty much we're going to complete this section over here in which we have learned how to calculate atoms or molecules. And the first thing to determine is look at the number of the number of moles that are required. Write a plan to convert moles to atoms or molecules, and use Avogadro's number to write a conversion factor. So let's try to do a problem up here in which we have how many oxygen atoms are in 0.15 moles of aspirin. What is given to us is we are given that this problem has 0.15 moles of aspirin, and what we need to find is the molecules of aspirin. So I tell students to read the question many times to see what you are required. It's asking how many atoms of oxygen are present in these many moles of aspirin. So you have to now come up with your plan. So for moles of aspirin, you need to know moles of oxygen from the formula, and then from there you will go to the atoms of oxygen. So let's look at the equality. The equality that we will use is 1 mole of aspirin has 4 moles of oxygen atom, as you can see from the formula. So these would be my conversion factor. And notice I wrote it down as 1 mole of oxygen is 6.02 10 to the power 23 atoms, because that's a standard value which we know. So now since we know all these 2 different factors, which is one set is this and one set is this. Let's go back. Remember, we have to convert moles of aspirin to the moles of oxygen first, and then from there you will go to the atoms of oxygen. So when you set up a problem, we want to do it in one step. So notice, now let's read it, 0.15 moles of aspirin. We're converting down to the moles of oxygen using my conversion factor. I keep the same unit on the bottom to make sure my units are converted to the moles of oxygen. And since I know 1 mole of oxygen is 6.02, again, notice these 2 are the same. So you will cancel this unit to this unit to this unit, and you convert your 0.15 moles to the oxygen atoms. We might do some problems in class too to reinforce these concepts. Hopefully you're understanding this. I think I'm going to stop here, and then we will do a second section in the next lecture. Now, in this section, we will learn how to do molar mass factors and how to convert moles to grams and grams to molar. The molar mass of an element or a compound is one of the most usual conversion factors in chemistry. Molar mass is always going to be the mass of the formula of that compound. So as you can see up here, this is methane, the methane gas that is used for cooking in gas heaters, and 1 mole of methane is equal to 16.04 grams. Again, 1 carbon is 12 atomic weight, and hydrogen is 1 each, so that would be 12 plus 1 times 4, so you would get 16 is the molar mass of methane. So let's do a problem in which we will convert some conversion factors. So let's look it up here. Acetic acid, the formula of acetic acid is given to you up here. Acetic acid gives the sour taste to vinegar. And we want to write an equality and the 2 molar mass conversion factors for acetic acid. So before I go to the next screen, I want you to think of it. Hydrogen, look at the atomic weight of hydrogen plus carbon, 2 of those, plus hydrogen, and there are 3 of these, plus oxygen, and that is 2 of those. And then we can come up with the total molar mass. So hydrogen would be 1 plus carbon is 12 times 2 plus hydrogen would be 1 times 3 plus oxygen would be 16 times 2. And you add all these up and you should get the value of 60.05 grams of acetic acid. So this problem can be now worded as 1 mole of acetic acid is 60.05 grams. So if I asked you how much would 5 moles of acetic acid be, then you would write down as 5 mole of acetic acid times. You will then decide which conversion factor to choose. And as I've told you, if you have moles here, you need to have moles on the bottom, which would be this one. So you would have 1 mole here, 60.05 grams over here. And if you multiply 60.05 times 5, and you should get 325 grams of acetic acid. So you can see how we use this conversion factor to determine how many grams of acetic acid is present in 5 moles. Now here's another problem in which we will convert moles to grams now. So for example, aluminum is used in building lightweight bicycle frames. How many grams of aluminum are in 3 moles of aluminum? So again, you are looking for moles, how many grams in 3 moles. Let's go back over here. Our plan is to determine 3 moles of aluminum has how many grams of aluminum. So let's look at the equality. We know that 1 mole of aluminum is 26.98. Even for your class, you can round this up to 27. That would be fine. And so you have these 2 equalities. And now you can set up your problem. So we have 3 moles of aluminum mentioned here, and we use the conversion factor to make sure that our molar of aluminum cancels, and you get approximately 81 grams of aluminum here. So these problems that I just did reinforced how you would convert. Knowing the concept of moles to gram, we can now determine any kind of moles can be converted to grams. I reinforce back again to this part, which is that you must make sure that you have your steps correctly done over here. The steps would be to find the relationship between the moles of an element to the grams, and then set it up accordingly. So this was the end of this mini section. As a matter of fact, I think I'm going to go ahead and do the percentage calculations on the same recording. So now let's look at percentage composition, which is expressing the mass of an element in a formula in a percentage. And this is fairly easier and a lot simpler than what we did with the moles. So for example, carbon dioxide is given up here. If we want to look at the percentage expression of the number of carbon atoms present in the mole, then notice I've got 12 grams of carbon. Divide that by the total weight of the molecule, which is 44, times 100, and this molecule of carbon dioxide has about approximately 27.29% of carbon. Same thing for oxygen. If you want to know how much oxygen it is, then 16 times 2 is 32. 32 grams of oxygen in the total molecule, which is 44, times 100. That gives you a 72.7%. So sometimes we do use percentage expressions in making solutions or making compounds, but mainly we use the moles. So for calculating percentage, you take the total mass of each element in the molecular formula, and you divide that by the total mass and multiply that by 100. So let's look at another problem in which we see what is the percentage composition of lactic acid. The formula for lactic acid is given to you up here, a compound that appears in the blood after vigorous activity. So what are we trying to find is the percentage of lactic acid. Step 1 would be to determine the total mass of each element in the molar mass of a compound. So there are 3 carbon, which would be 12 times 3, 6 hydrogens, 1 times 6, 3 oxygens, 3 times 16, and you have the value. Now for your calculations and your tests and exams and quizzes, you can do an approximate. You don't have to do the decimal places. You can use a whole number for these problems. So this would be the total mass of each element in a formula for lactic acid. So now if we had to, let's go back. I don't think I finished it. What is the percentage composition of each element in there? So what you would now do is take the 36, which is of carbon, divide that by 90 grams, which is the total weight, and this is carbon times 100, and this will give you your percentage. So 36 times 90 times 100, and that comes to 40%. Similarly, for hydrogen, you would do 6 grams of hydrogen. Total is 90 grams of lactic acid. So times 100. 6 divided by 90 times 100 on my calculator comes up to 6.6%. And oxygen would be 48 divided by 90 times 100, and that comes to about 53.3% of oxygen. So each of these, I think the percentage solutions were a lot easier than your molecular weight problems. So we're going to stop here, and we will have a continuation on the next section.